For this video, we will cover an introduction to light and electron microscopes. Let's start out with a quick comparison of the pro and con of the two. Comparatively, light microscopes are relatively cheap, about $1,200 to $1,600, but their magnification is not as great as seen in an electron microscope. Conversely, electron microscopes are very expensive, with some of the cheaper options costing about $50,000, but their magnification is much greater than what we can achieve with light microscopy. Since the cost of electron microscopes is so high, we won't play with those in the lab, so let's just cover a bit of information about the two types of light microscopes you could see in this lab. The one that we will use the most, and the one you're probably the most familiar with, is the basic compound light microscope that we use to visualize slides of prepared specimens. We do also have what we call a dissecting or stereoscopic microscope, which has less magnification but can be used to view samples in three-dimensional images. Light microscopes can be either monocular or binocular, meaning they have one or two eyepieces, respectively. Some microscopes are simple, meaning they have a simple lens, but the ones that we use in the lab are compound, meaning they have two lenses or more. This does bring up the consideration of total magnification, as both the ocular and objective lens magnifies the sample. Total magnification is calculated by taking the magnification of the ocular lens multiplied by the magnification of the objective lens. Most microscopes have an ocular lens of 10x, which makes the calculations pretty easy. So the four objective lenses on our microscopes are the scanning lens, which has a 4x magnification, low power, which has a 10x magnification, high power, which has a 40x magnification, and oil immersion, which has a 100x magnification. So to get the total magnification, we can break it down like this. Scanning would be 4 times 10, which is 40x. Low power would be 10 times 10, which is 100x. High power would be 40 times 10, which is 400x. And oil immersion would be 100 times 10, which is 1000x. Now, just in case the ocular lens is not 10x, let's try an example where the ocular lens is 5x and the high power lens is 40x. What is the total magnification now? We would just do 5 times 40, which is 200x. Another thing to be aware of with the different objective lenses is their overall size. The greater the magnification, the longer the lens is. This in turn decreases the working distance, or the distance between the lens and the sample, meaning you have to be more careful not to scratch the longer lenses. Another consideration with light microscopes is the resolution. Resolution refers to the ability of the lenses to distinguish 2 points. If a microscope has a resolving power of 0.4 nanometers, it can distinguish between points at least 0.4 nanometers apart, but anything less than that would appear blurry. Generally, shorter wavelengths of light provide the greater resolution. To calculate resolution, you should use the equation R is equal to 0.61 lambda, which represents wavelength, divided by the numerical aperture. So if you have a wavelength of 500 micrometers and a numerical aperture of 0.4, we would do R equals 0.61, 500 in parentheses, divided by 0.4, and we should get 762.5. Another consideration with light microscopes is what we call the refraction of light. Light bends to a certain degree when it hits a new medium, for example when you put a stick in water, and at very high magnifications this can decrease resolution. So in order to combat that, we use immersion oil. Note that this should only be done on the oil immersion lens, as the oil has to be removed after the use or it could damage the lenses. The basic way the oil works is that when light hits the sample, it helps direct it into the lens so we get the full image of the sample and little light is scattered. So we use the immersion oil to increase resolution and decrease light refraction. Another thing to be aware of with our microscopes is that images are seen flipped and reversed. So the number 6 would look like a number 9, or the number 7 would almost look like an L. Also, the direction that the slide moves is opposite to the movement of what is seen. So if it looks like you're going to the right when you view down through the microscope, it means you're actually moving the stage to the left. Lastly, we also need to know how to calculate the relative size of a sample simply by looking at it through the microscope. Note that the conversion between metric units is covered in a separate video. Now, in order to tell the relative size of a sample, we need to know the field of view. The field of view is simply what you can see as you're viewing down through each of the specific objective lenses. You can use a specific microscope slide that have very small rules on it in order to see the field of view for each objective lens, but that would just be too easy. Instead, we're going to calculate field of view by using what is called the FN number. This is generally 18 and can generally be found on the eyepiece on your microscope. So you can take the FN number and divide it by the objective magnification to get your field of view. So our scanning lens would be 18 divided by 4, giving us 4.5 millimeters as a field of view. Low power is 18 divided by 10 for 1.8 millimeters. High power is 18 divided by 40 for 0.45 millimeters. And all immersion is 18 divided by 100 for 0.18 millimeters. So if a question asks you how big an object is, let's say it takes up half the field of view and you're on the low power lens, you would say 1.8 millimeters divided by 2 means the sample is 0.9 millimeters long. All right, let's go ahead and wrap up with 2 more terms we do need to know about our microscopes. Our microscopes are parfocal, meaning that the specimen that we're looking at will stay relatively in focus when we increase magnification. For example, going from the 4x objective lens to the 10x objective lens. As such, once we increase magnification, we should only use the fine adjustment knob from that point on. Our microscopes are also PartCentric, meaning that whatever specimen we're looking at will be relatively in the same place or within the center of our field of view when we increase magnification. This concludes our video covering an introduction to light and electron microscopes.